Hello everyone, my name is Sherry. I'm from NTU, and I'm glad to be here to share our research on optimizing urban heat island mitigation, trying to propose a regulatory guideline for a sustainability city planning. And my advisor is Professor Zhang. And here's today's content. And in recent years, urban heat island is a critical issue for cities. City will have higher temperature compared to a suburban area, and urban heat island is mainly related to climate change and urban development. And from the previous research, they found that city will have higher temperature from 3 degrees to 10 degrees. So and urban heat island also have some impact to the city, like it decrease the air quality or increase the water and energy consumption. And also it will compose the outdoor thermal comfort for pedestrian level. So to solve this problem, there are some mitigation methods have been proposed, like urban planning intervention includes the building height changing and green roof ratio applied to decrease the UHI. And on the building design phase, there are roof design or green facade applied to the building, also trying to reduce the UHI. And from the previous mitigation method proposed, our research object is trying to using the CFD simulation to analyze how these mitigation really affect to our study area. And this is our study area in Taoyuan. And over there are some existing nature source like the pond, the canal, and the creek, but most of the land are not developed yet. So we are trying to propose a urban planning for this area and this urban planning is trying to reduce the UH effect exerted by regional development after we develop this area. And finally, we will propose a guideline for this sustainable city planning for the government. And these are our workflow. First, we will try to analyze the urban situation of that area. We will analyze the climate condition as our simulation input. And then on the second part, we will test on parameter to see which scenario will have most good impact. And then after that, we will use the scenario or parameter that we found in the second part to propose a solution case and to see how all of the mitigation methods apply to the study area, how much degree we can reduce compared without any mitigation method. And these are the weather station near our study area. The orange part is the study area, and there are 5 weather stations near our study area. And after the analysis, we use the in July. And the second part, we are going to analyze how each mitigation method can affect. First, here is the baseline case that is without any mitigation method. You can find that there's some hotspot in the simulation, in the research area. And in the middle of that is the pond. And that is in the middle of the day. And here's the situation in night. First, we will focus on the building height and green roof. And after that is the roof design and green facade. And we test on two different area. For the building height, we test on 4 different of building height from 20 meters to 75 meters. And these are the model that we built to run. The result that we examine is on the 1.5 height above the ground, because these are the mainly pedestrian level. So we want to see how they affect to how these scenario affect to the pedestrian. And these are the simulation results. we can find that the higher building will have more lower PET and AT. We can find that over there is about 20 meters high of building, and it's about 35 degrees along the street. But if we increase the building height to 75 degrees, it will reduce to about 74.5 degrees. So the building height really can affect the air temperature. And then secondly, we test on the green roof ratio. We also set different kind of parameter from 50% of green roof ratio to 100% of green roof ratio. And the white part here is about the area that we put the green roof. And here's the result. And these graphs are comparison to the baseline that is without any green roof ratio. And we can also find that the higher green roof ratio will also have more higher air temperature decrease. Like if we apply all of the building with green roof, it will have more lower temperature. And the maximum decrease is about 0.2 degrees. And another parameter that we test is the roof design. We test on 3 different kind of roof, from cool roof, green roof, and PV roof. Cool roof is a kind of paint that we apply to the roof. And here's the result of these parameters. In the green roof and cool roof part, we can see that they all can decrease the air temperature. But in PV roof, it will have increased the air temperature here. And the last parameter that we test is on the green facade. And the green part here is that the place that we apply the green facade. And the simulation result, we can find that the place with air temperature decrease is similar to the place that we apply the green facade. And here's the vertical cut. Like we can find that the red one cut is this way, and this blue part is lower air temperature distribution place, and it is the same as the where we place the green facade. And for the part here, we did not apply any green facade here, so we can find that they actually have more higher temperature here compared to the place that we applied the green facade along the canyon. And for the last part, we are going to apply all of the findings previously to propose a solution case for this study area. And these are the highlights of the study area that we applied to the solution case. You can divide it into 4 parts from wind, water, and architectural landscaping, and the green belt. And let's go to the detail. And these are the simulation model that we built. Actually, they look the same in overall, but in detail, they will have some difference, and we will go through it one by one. First is the water pump in the middle of area. And from the video, we can find that the pink part means that there's no air temperature difference compared solution to baseline. Baseline is without any mitigation method, and the solution one is with mitigation method. And pump can actually reduce the air temperature about 0.5 compared to without any pump, like the up-one model. And the wind direction of this tank is from the west. So on the downwind side of the pump, it will affect by the pump. And also there's a cooling island that we placed on the upwind side over here. And the air temperature distribution also show that the air water with cooling island here have more lower air temperature compared with the surrounding buildings. So these 2 water bodies actually can reduce the air temperature. And another one we are going to analyze is on the wind side. And here's the first one is the row width of the primary breezeway. From the baseline, we can find that we did not apply the setback on these building. They are along the street. But in the solution one, we set the building on setback, so it will have more wider for the wind to blow through it. And here's the 3D simulation model how to see how the wind really went through the Lake Canal. And here we can find that the place we set back here, the blue one, it have more low air temperature compared to the baseline. This is the air temperature comparison, baseline and solution. And it also can increase the wind velocity here, like if the purple shows that more higher wind velocity compared to baseline. So this also have can affect the UHI. And another one is the constraint maximum building width around the pond. And for the building baseline model, the width of building each one is more closer, and the solution one is that they will have more wider building destination of each one. So the more wider, then the wind can flow through it. And here's the simulation result. We can find that on the wind direction from the east, the solution one can increase compared to the baseline because we have more wider building width with each other. And from the wind direction of south, it also can show that the wider building width of each one can increase the wind velocity. And another highlight of this research is that we apply the breezeway on the ground level. We can find that there are some walkway on the ground level. And here's the simulation result. Over here, the wind velocity can really blow through it. And here's a video how they would really flow through the breezeway of ground level. And a vertical cut of here is a green balcony, how they affect on air temperature. We can find that they'll have about 0.5 degrees over here with green balcony applied here. Yeah. And another one is a social housing green roof over here. The place that with more air temperature decrease is that the place with green roof, same as here. And another one is that we also apply a greenery to our school. So here is the school. We apply some green roof here. So it also have air temperature decrease here. And this is the vertical greenery of the social housing. We apply the green facade on the wind direction. Here we can see like along the street, they will have low air temperature compared to baseline. And another one is the green pathway. We set all the trees planting along this street. And here is the street. We can find that the wind air temperature distribution is more lower over here because of lots of greenery on that street. And here is the video of comparison. The left-hand side is air temperature distribution comparison, and the right-hand side is the wind velocity comparison. We can see that through the day difference, there are small difference changing here. In the night, the mitigation will not have too much impact to the study area, but in the morning, it will have higher temperature. You can see that here, it's not that good, but if the time change to the morning, it will have more air temperature decrease here, and also same as wind velocity. And after that, we will have comparison numerical analysis. We first analyze on the left-hand side of study area. The maximum decrease of left-hand side is about 0.45 degrees. and the average of this area decrease is about 0.1. But the number is reduced because some of the area is not have no air temperature changing, but we use average, so the number will be small. And these are the in the middle part, also about 0.45 and 0.22. And on the right hand side, here's the result about 0.225 degrees and 0.22 degrees air temperature decrease. And these are the comparison of PET and some 3D models. And here's a graph of all the highlights that we apply to this study area. But there are some limitations in this research is that our planning might differ from the government because some land use restrict or something. So we will have to convince the government to use our purpose of urban planning. And another thing is that the weather condition will also affect the urban heat island mitigation, like it will not have that much impact in the winter of these mitigation methods. And also, if we want to apply these mitigation to other countries, we will also need to reanalyze the weather condition of that countries. And these are my reference. Thank you.